Oh, yeah. Oh, yeah. No, like, it's not beautiful, like,
I believe that result.
Okay.
What is that?
All right.
I don't know. We could do something. Theoretically.
Okay. So we looked at damping. So we added friction to the system. When we added friction to the system, force equals ma. The forces are now not just the spring force, but also a resistive force. So I put FR just because damping is kind of a resistive force, either air resistance or friction or friction or it could be electrical resistance, which we'll cover later. So this additional resistive force is going to be a force that's proportional to the, let's listen. It's proportional to the derivative. So that means it's going to be proportional to how fast you're moving. So the faster you're moving, the greater your resistive force is. Like if you were sticking your hand outside your car when you're driving, the faster you're driving, the force against your hand will be in the opposing direction, so be opposite to the direction you're moving. So if you're moving this way forward, the force would be against your arm. But you're gonna feel like you'll need to like work harder to keep your arm straight when you're driving, like if it's like a race car versus if it's just your a small like bicycle or something. So that's that. And then so we looked at that, but it's going to depend on how big your delta is. Your delta is your resistive force. So like how, in the case of the table, how sticky your table is. And so in general, your differential equation will be of this form, where you have a mass damping and the spring constant, and you'll solve the characteristic equation. And if we just let m and delta and k be anything, then your quadratic equation will give you your r, and there's going to be distinct real roots, complex roots, or repeated roots. And the complex roots will, okay, so it just depends on what the sign of this red box is. This is called a discriminant. So if your delta is quite big, that means your damping is quite big. That means your resistive force or friction is pretty big compared to the mass and the spring constant. Then that means your delta squared is really, really big. So because of delta squared being really big, this quantity in here will be positive. And that just means you have a lot of damping going on because delta is big. And that's going to be like what we just saw up here. You'll have two distinct roots. The solutions will be exponential decays. Just means that your friction is so big that it's like this table is pretty sticky, and it'll just like move slowly back. Like you might have pulled it out, but it'll just move slowly back to initial position without like bouncing back, because it's so sticky that it'll just slowly move back and stop. That's called over damping. Or it's called over damped motion. It's like the friction is so big that there's just zero oscillations, and it just like slowly just moves back to its equilibrium, like natural length of the spring, and then it just stops there. Now, if you had the case where delta is really small, that means delta squared minus 4mk will be negative if your delta is quite small. That's a situation where you have very little damping in your system. That's going to result in this quantity in here being negative because delta squared is quite small, and you're going to get complex roots. Your solutions will be basically like looking like this right here. So I just wrote it down here. It's going to have a real part. The real part is going to come from what I circled in orange here, negative delta over 2m. That's going to be like your alpha. It's going to be negative delta over 2m. Your beta is going to come out of this part right here. It's going to be the imaginary part that's going to come out of here. Of course, there's going to be an I that pops out, but that's going to be your beta. that's going to determine how quickly it oscillates. But what I want to focus on is the fact that the real part of our root will always be negative, because you can't have delta and m be negative, because you can't have a negative damping constant, because then it'll it'll do the opposite of resistance. And then you can't have a negative mass. So because of this negative sign with all these being positive, your alpha will always be negative. You'll have sinusoidal like motion. So these cosine and sines will make your thing oscillate, but they'll be multiplied by a function that is exponentially decaying, because this alpha is negative. So you're going to have an amplitude that's exponentially decaying. And so you can actually compute the magnitude, because you know your magnitude of your amplitude, your amplitude is C1 squared plus C2 squared all square rooted, but there will be this extra factor in front due to the alpha being not non-zero. And so your solution will look like something that oscillates but decays. The oscillations would decay. This is a situation where when your delta is pretty small, you'll get this negative inside the square root, gives you these complex roots, which gives you oscillations will still stay, but it will decay. The reason it decays is if you think about this spring mass system, without friction means that it's slippery, it'll just keep going back and forth forever. But if it's got a little bit of stickiness to the table, then it's going to oscillate, but then it'll just be like, so it might be like this, and then it'll slowly oscillate less and less and just kind of just stops in the natural length of the spring. This is called underdamped. Underdamped because compared to the previous case where delta was really, really big, where it was so sticky that it didn't even oscillate at all, it just moved back and stopped. This is a situation where it didn't damp the system enough to get rid of all the oscillations. So there's residual oscillations still left, but it's still damping it. So eventually the oscillations will die out, but it doesn't die out immediately. So like compare the graph from this is over damped, where the solution form is qualitatively a lot different because it's just exponential decay terms. It just like slowly moves back because there's so much friction that it doesn't even have enough force to like bounce back and forth anymore. It just moves back. Whereas, so that's over damped, a lot of damping, versus under damped is where the oscillations have not been fully damped out. It will oscillate less and less and less and then just stop eventually. And that's called under damped. That's whenever this quantity in here is negative. And then there's a transition point between when delta squared is greater than 4mk and then when delta squared is less than 4mk. There's an instance when delta squared is exactly equal to 4mk. That's going to make this red quantity in here be 0. That's going to be the case where you have repeated real roots. So one of them will be like e to the, RT, and then the other one's going to be TE to the RT, right? This one, you won't have sines and cosines in your solution, so it'll look like kind of like exponential decays. It's going to be like the transition between underdamped and overdamped, and that's called critically damped. I guess maybe critical because, we're used to seeing like something equal to 0 is a critical point or something. So whatever's in here is equal to 0 will be the critically damped motion. It's going to look more or less like this graph, but this graph is like the table is so sticky that it just slowly moves back. The underdamped is like, it's not that sticky, so it'll move back quickly, but because it moved back quickly, it'll overshoot, and it'll overshoot and come back like this. Critically damped would be kind of like you got the thing to move quickly back. So it wasn't sticky enough to be slowly moving back. So it moved quickly back to the natural length, but it didn't move quickly enough to like shoot past it and oscillate back and forth. So this might be like if you were trying to engineer a system where you want the system to return back to its natural state quickly, then you might create a spring that has a certain kind of K or a resistive force delta that has a certain damping that will result in delta squared equal 4mk to equal each other, or equal delta squared and 4mk to equal each other, this to equal 0. Like, let's say you have like a truck and a suspension spring or something, and you're like thinking this might like bump into the road, but you want the car to actually like have the body just like return back to its natural position quickly right after it might be shocked by a bump. then you want either your spring for constant, your stiffness constant K, or if it's a hydraulic spring, like maybe there's like some fluid inside that you want to cause damping, that will result in a critically damped motion. So it just returns back to its equilibrium position very, very quickly. You don't probably want it to be under damped because then it'll just be like bouncing back slowly back to its, but you want it to actually come back quickly back to its original state. And so you have the M you probably can't control because that's like the mass of your truck, but you can control the stiffness constant of your spring, your suspension spring, or if it's in some kind of hydraulic liquid or something, then you could control the damping for that. But so you know these are parameters you can tune to determine what kind of motion or force certain kinds of motion in your system. So like this is underdamped is going to have some oscillations left that decay. Critically or overdamped are going to look kind of like this. And it's going to also depend on what your initial forces are on this. So like your initial conditions might be different depending on. So like let's say you had like an initial like velocity in the spring that you just like pushed it out by like some x prime of 0 is greater than 0, then it'll go up and then come down. Or you might have an initial nudge to this that's negative. That means it'll shoot down. If you really push it negative very, very strongly, I'll do double less than, then it will, even if it's overdamped or critically damped where you have enough friction to like damp out all the oscillations, it may overshoot and then return. So that's that. So let's look at, so that's just horizontal spring mass systems with just the spring force. And then we also added damping, which is the resistive friction in that case. Now I want to add another force to the system, which you can do easily by flipping the system vertically. Because if you were on a table, then there's really no gravity. But if you have a vertical spring system, you're going to have all of this be subjected to a gravitational potential. So that's like a constant external potential force. So we're going to define a new variable because it's a vertical system now. We'll use y, and then we'll use the same convention we had before where you stretching. So that means like if you were to go down, will be actually positive. So let's say y equals 0 corresponds to the natural length of the spring. So that's like the same as we had before. That's as if you just took off the mass and you just let the spring hang on its own, how long that would be. That's the 0 position. And then positive downwards, which is probably less intuitive because, you know, down you might think is negative, but we're going to still keep the convention that stretching the spring is positive. And then negative will be upward. Using that convention that down is positive, then your force due to gravity will just be F sub G, because I'm going to use a subscript G for gravity, is equal to mg. You might be used to seeing negative mg, but if we're using the convention that down is positive, then it's just positive mg. And m is the mass of the object, and g is the standard acceleration due to gravity, which is depends on the units for the problem, but it could be 32 feet per second squared, 980 centimeters per second squared. I mean, if you convert it to 980 to meters, it would be 9.8 meters per second squared. But that's just how it is in Earth. And then it's going to be proportional to how massive your object is. That's going to be your gravitational. So let's recall Newton's second law. Newton's law, F equals ma. Now we're using y as our coordinate. So that means that you're just going to have a is equal to y double prime, and then you shove it over to the left, and you'll just get m double prime equals f, where f is the total force acting on the body. And in this case, we have F right here is the total forces that are all acting on the body is going to have 3 things. We still have a spring, so it's Fs, that's spring force. We still, in this case, I guess it's not as much friction, but maybe like air resistance or something. So there's some resistive force. And then there's also gravity. And each of those, we know like f of s is equal to negative ky. I mean, it used to be negative kx, but now it's y because we're using y instead. We know that the damping force is proportional to the y prime, the derivative of your position, plus Fg is just exactly this new force that we're introducing. So I'll just circle this and then say that's this one coming into here. And then if you shove all the terms with y and y prime to the left, you'll just get this. There's an mg that's still left on the right. That's actually your, now it's a non-homogeneous, right? So because of the fact that we have this term on the right, it's not homogeneous anymore. It used to be homogeneous, like before we didn't have gravity. It was mx double prime delta x plus kx equals 0. But because of this extra term mg that doesn't contain y in it, we're just going to leave it on the right. This is a classic second order constant coefficient with a constant forcing function. And the constant forcing comes from your constant gravitational potential force. All right, so there's a constant gravity force that's acting in the system. And so you could solve this using, you just use method of undetermined coefficients, right? What's your particular solution form? Your particular solution form will be just another constant. And then you just solve the homogeneous problem and you just add the particular with the homogeneous solution. This will give you the motion of your vibrating a mass with respect to 0 corresponding to the natural length of the spring. So the natural length of the spring being like if you took off the mass off the spring and you just let the spring be whatever length it naturally is, that would be your origin. And then it'll give you your motion with respect to that where down is positive and up is negative. So that's fine. You could do it that way. But a lot of people, they actually redefine a new coordinate system. And the motivation for redefining a new coordinate system is that if you do that, you can offset the coordinate system by some amount that will make this differential equation, due to this change of variables, become homogeneous. Right now it's got an mg on the right, so it's non-homogeneous, but you could actually shift the coordinate system by a little bit to cause this differential equation to be homogeneous, and people would prefer that because it's easier to solve a homogeneous equation. So in our current coordinate system, y equals 0 corresponds to the natural length of the spring. So that's it. That's this right here. So I'll just label that this right here is currently our system is, I'll just underline in blue here. Net y equals 0 corresponds to the natural length of the spring, which is like saying take off the mass and however long your spring actually is naturally without being stretched due to the mass. That's the y equals 0. That's what we're using currently, just because that's what we also used before when we had a horizontal spring mass system. Now, what if we, instead of saying that this is my 0 position, what if we let the origin, so that means our 0 position, be a bit lower? So let's say we attach the mass and we just let it rest, let the mass stretch the spring. Obviously, if you put the mass on the spring, due to gravity, it will come down, and you just let it stay like that. And let's say that's our new 0 position. So I'll just write that that's basically like saying the equilibrium length of the spring, that's a stretch due to the gravity. So why don't we create a new system? I'll just use x is equal to 0 and then say like that is going to be our new position. That's our new 0 position. So it's like so there's a difference here. Y equals 0 is like the position due to it's the position corresponding to the natural length of the spring that's not stretched or compressed. This right here is not the natural length of the spring in the sense that the spring has been stretched. But you could still call it like the equilibrium length of the spring that would have resulted if you just put the mass on there. You're not letting it shake or anything. You're just letting it pull it down and then stop and then see like how far that was. So if you do that, then suppose if you do that, there is this slight stretching that has occurred right here, and I'm going to call that delta L. Right? This is like L plus delta L. There's an extra little bit of length that you had that's caused by gravity. And so let's say delta L is the extra length beyond the natural length of the spring that gravity stretches. And you can actually compute what that delta L is if you know like your spring constant and your mass, and we also know gravity. It's actually going to equal, this is always going to be true. What's happening here is that you have a spring force, right? So your spring force, remember, was is like something like this. Your spring force is equal to KL. I mean, I guess you could say negative KL. So it like or negative kx, but you know, we are thinking of it as like the longer you stretch this, right? So like if this delta L, that means that you haven't stretched the spring at all. So delta L is 0, then the spring is happy. It's just not going to do anything. But the further you pull this down, that means your delta L is 0, but you're actually making it bigger and bigger. So let's say like delta L is equal to 3 or something. There's going to be a spring force that's acting on it. And in this case, it's going to be trying to pull it back up, right? And the larger your delta L is, the larger your spring is being stretched, the greater your spring force is. Because let's say your delta L instead of 3 was like equal to 10, then that means like you're going to have a spring force that's K times 10 upwards, right? So what's happening here is that like how much it stretches, the delta L that it stretches is going to be a balance between gravity and the spring force. So the spring force is going to try to pull this up by K delta L, whereas the gravity is trying to pull this down by mg. The more the gravity pulls it down, the more the spring is trying to counteract and actually pull it back up, because spring force is proportional to how much the spring is stretched. So the gravity will initially stretch it a little bit, and the spring will try to counteract, but the gravity may still be stronger, so it'll pull it more, but then spring will try to pull it up more. And then the further it goes, there's going to be a point where gravity can't keep pulling it down because spring mass is also going to get higher and higher as you stretch the string more. And there's going to be a point where they're in balance with each other. And that balance, that force balance is this right here. So there's a point where you have these two are equal to each other. The K delta L and the mg are in opposite direction, but equal. That'll give you your L, the X delta L, the extra length that your spring must have stretched due to gravity. Engineers actually determine K, the stiffness constant, using this idea. So you know, you might take a spring and you look at it and you're like, I don't know what the stiffness constant of this spring is. That's usually very difficult to tell by just looking at the spring. I mean, if it's really thick, then maybe it has a very high stiffness versus like not very thick. So like just by looking at a spring, it's difficult to tell the spring constant or the stiffness constant. But you can always hang it on a wall, on a ceiling, or not, you know, whatever, some kind of thing, and then put a known mass. So you just be like, I know this weighs 500 grams. Stick it on the spring mass. You know gravity. So you know m, you know g, right? Because you know gravity, you know you're putting a known mass onto the spring, and then you measure delta L. See how long it stretched. Then you can use this equation to compute K, the stiffness constant. The larger your delta L was, that means like, you know, if you were to solve for K on this, it'll be like K is equal to mg over delta L. The larger your L is, that means it stretched it more, the less stiff your spring must have been, because you're dividing by a larger number in the denominator, right? Which makes sense, because if you're a very stiff spring, then your delta L should be small because you're not able to stretch it that much. So that's how in practice people would probably measure the stiffness constant of a spring, because that's hard to see just by looking at it. But you can do these measurements and then see. This is basically the force balance between the mass, the gravity, and the spring force. So now we know how much it must have stretched due to gravity, and let's now define a new new coordinate system X. Now we're gonna, like I said right here, like we're gonna have y is equal to 0 here. Let's define a new coordinate system using X, where X is equal to 0 corresponds to the equilibrium length of the spring. So let me just use red. So this is like, I'm defining a new coordinate system. So this is now our 0 position. and I'm going to use x's. And so how do you convert between the y coordinate system and the x coordinate system? The conversion will be due to this. This will give you your conversion. Why does this make sense? Well, let's just think about what this position right here would have been like right here is x is equal to 0. So let's just say here x is equal to 0, right? But if we use the y coordinate system, then this position would have been what? It would have not been 0. It would have been, yeah, plus the delta L. So it would have been like 0 plus the delta L. I mean, we don't have to write the 0, but I'll write the 0 plus. So this is like saying we're using a new coordinate system where we're going to call this the 0 position, but with respect to the original coordinate system where y0 was not the equilibrium length, but the actual natural length of the spring, this would have been 0 plus delta L. And so that's why this formula makes sense, because it's like, how do I convert from x to the y coordinate? Well, this position, x was 0, y was delta L. And so this relationship is the correct relationship that converts between your original y coordinate system and your x coordinate system. You literally see that it's just a shift of delta L one way or the other. So if you're trying to go from x to y, then it's an addition of delta L. If you want to go from x the other way around, it's a subtraction of delta L. So it's really just some vertical shift that is due to the extra length that is stretched beyond the natural length of the spring, coming from the balance between the spring force and the gravity force. So now this was the differential equation we had before. So I'll just use purple. So this right here, right? This is like all this equals mg. This is the starting point. Now I'm going to do this coordinate transformation. So, or basically this change of variables here. So what's going to happen is that every single time I see a y prime or y, I'm going to stick this new change of variables in there. So that means that my double prime will be m times x plus delta L double prime plus delta, this y prime would be like this x delta L prime plus k, and this gets plugged into the y here. Now, what do these, like, I'm just literally plugging in y is equal to this into all the y's, and what do these mean? So if you have, for instance, like this x is equal to, all right, here, x plus delta L is double primed. This is the same thing as saying you have, it's like saying take the second derivative of x plus delta L. So what does this mean? I just take the second derivative of x, because derivatives are linear, and linear operator, so you can actually just apply it to the first plus to do it to the second one. So that means you just have, this is the same as x double prime plus, what's the second derivative of delta L? Well, delta L is just a number. It's like the however much it's stretched. So that's just a constant. So if you took the second derivative of constant, it's just 0. So that's why you have this quantity right here is just equal to the x double prime right here. Okay, same idea with this one. X plus delta L prime would just be x prime plus delta L is just a number. So that's a constant, so it'd just be x prime. This one, you're not taking the derivative of, so it'll just stay just like this. Then you distribute the k to each of these. So it's be all of this top plus kx plus k delta L. But what did we say k delta L is? K delta L must have been mg, right? Because that's, so basically that's going to mean that this k delta L is mg. That's because we compute, well, the delta L comes from this being satisfied. So it means that these two quantities here are going to cancel each other. So I'll just do this, and this will cancel with this right here. Because K delta L equals mg. They're both like the same thing. So you could just subtract from each other and then they'll just be this. And so now with the coordinate transformation, where we made this change, the original equation with respect to y was non-homogeneous, has now with respect to the new coordinate system x has become homogeneous. So you could now solve this homogeneous equation, but your solution will give you position of your object as it oscillates, will now be with respect to motion with respect to the equilibrium position. So it'll be with respect to this being the 0 position. That means like if you took this mass and just attached to the spring, it'll just naturally stretch to some amount. Your solution will give you oscillations with respect to that position rather than the position that would have happened if you had taken the mass off and just looked at the natural length of the spring. So your 0 position will be different. So you just have to keep that in mind. But if you use that new 0 position, your solution, you can just get away with solving the homogeneous equation. So this is like a big if. If we measure the position from the equilibrium length of the spring that's stretched due to gravity, some people call that the rest position, then you can just solve the same homogeneous differential equation that we had been solving before with the horizontal spring mass system. Okay, and that's pretty common for people to do. They'll just be like, well, basically it's going to act like a horizontal spring mass system where the horizontal spring mass system was vibrating with respect to the natural length of the spring, which is like how much it would have been if it didn't stretch or be compressed. It's going to oscillate around that. So basically it's just kind of vibrating around that position. But if you flipped it vertically, it's going to qualitatively, like physically, your intuition might be like, it's going to kind of do the same thing, but it's just going to oscillate around the position it would have been if it just been stretched due to gravity. So like you just let it stretch and it'll just like bounce around that position. There's no reason to believe that it'll bounce way up here. It'll bounce like where it had been stretched, with that being the 0 position. And so so this is still a homogeneous equation when you do that. But I'm going to now throw in more forces into the system in a way where we're going to have to solve a non-homogeneous equation. So so far, all the forces we looked at, spring force, damping force, and even the gravitational force, are all forces that physicists and engineers would consider something that still can be solved by a homogeneous equation. With the gravity case, you can still use the homogeneous equation because you could do that coordinate transformation and it still reduces basically to solving a homogeneous equation. And people call that the free response of the spring mass system. But how can you get a differential equation that will need to be non-homogeneous? So if you look at your F equals ma equation, you have all these terms that we ended up introducing, right? We had like Fs, Fr, Fg, but what if we add another force onto this that's like just purely some external force that's non-constant? Now, it being non-constant is going to be key. So that's why I have F of t. One could have a force that's, dependent on the actual position of your object, but that would make it a harder problem. So let's just make the external force be only time dependent. So it's not a constant force like gravity. Gravity is like just always a same force the whole time. But what if you have an external force that's not constant? It would be like as if you were in an earthquake or something and you have like this, or you might have the spring mass system attached to the top of a box and you're shaking the box. Or there could be an electromagnet that's like basically attached to this mass, and then there's like a magnetic force on the top of the ceiling that is like turned on and off or something. And that's some kind of oscillation of the attractive force between the mass and the ceiling or something like that, or you could shake it. It's a time dependent, so it's like you're just like shaking at some certain amount of frequency, or you're turning on your magnet on and off at a certain rate. So it only depends on time, but it is non-constant. Then your differential equation will look like this, because essentially you'll have another forcing function that is time dependent that will stay on the right-hand side. And this is called the external forcing function or input, which of course we've been saying that the whole time in this class. And then you're going to have some kind of solution to this that's going to have to account for this other external force. And let's consider an additional external force, this F of t, being like some oscillatory force. So we'll have like, well, let's make this force, that's the thing that you're shaking, or the earthquake or whatever, be like described by F, capital F, cosine of omega t. We've seen omega naught t in the past. Why is this not showing up? So I'll just write here. This is supposed to be omega. Omega is called the forcing circular frequency. So like this is like how often is going to be it's going to it's going to describe how quickly you're shaking the object. That's just an external force. And so this happens in real life, right? So like you might have a bridge that's like actually shaking, not just it doesn't naturally shake like this, I mean, it's not supposed to shake like this, but it might shake like this because you have wind or maybe cars driving on the bridge that causes it to shake. These are called external forces. It actually broke. This was back in 1940. And maybe there, models that could simulate this if you like had like, oh, this kind of bridge will be in an environment where there's going to be these kinds of winds, and then how the traffic might flow on this will actually cause it to shake. It's probably hard to see, but these buildings are shaking a little bit because of the earthquake. This is obviously simulating an earthquake, and I guess they're trying to compare like one kind of building versus another kind of building. It looks like this one has something in the basement that's trying to mitigate the shaking, which obviously is very important in a country that may have a lot of earthquakes. But you're going to model these by, so this shaking of the table, this hand moving it, that's like that's like this right here. That's like your FT right here, that little F of t on the right. And you could probably model it as like this kind of thing where how far your shaking amplitude is, your capital F, and your omega is like your frequency of your shaking. And then you want to know, the position of this object as a function of time subject to this kind of shaking. This is just people driving in the car, and your car could be shaking because you're like on a bumpy road. Those bumps are going to cause an external force to your system. And so these are examples of forced vibrations in real life. So let's look at what would happen if we include that kind of force. So in practice, there could be friction, but let's just look at no friction. So we'll go back to no friction. So delta is equal to 0. Let's look at a vertical spring mass system, no damping. Let the mass be 1 gram. And then if you left it hanging, you observe that the delta L, which is the extra length that the spring stretches by, is equal to this 980 over 9 centimeters beyond its natural length, spring length. And then you want to find its spring constant and use the acceleration of gravity, and that will allow you to come up with the differential equation that you need to solve for this system without any damping. So how would you find K? It just goes back to this the force balance equation. So remember, we saw that K delta L has to equal mg if for a vertical spring mass system. And then you need to find K. This is how engineers find K, right? So this is like, oh, I measured this. It looks like the length, the delta L was 980 over 9. M is, well, 1 gram. So I put a 1 gram thing onto this spring. And we know that the G is equal to 980. I use G is equal to 980 because if you look at your units for this, you just have to make sure that the units are consistent. So like if you have delta L is measured in centimeters, you see that from here, then your mass is in grams. Then your G will, because of this centimeters right here, you probably want to use 980 centimeters per second squared. This will give you K has to be, because there's a G on this side, there's an S squared on this side, K will be in the units G over S squared, which is what they say right here. So just G could be 32 feet per second squared, could be 9.8 meters per second squared, could be 980 centimeters per second squared. I mean, there's like many ways to describe G depending on the units you use, but you just have to make sure that it's consistent with the rest of the units in the problem. Yes, what? Yeah. K will equal 9, yeah. So if you actually like did this, K will equal 9. The units would be like grams per centimeter squared, but that's not important. Well, that's important, but we won't need that once we build the equation. The differential equation is mx double prime. Because delta is 0, I'm going to skip that term, and it's going to be kx is equal to 0. Or no, is equal to, here, it says use the vertical coordinate system. So this is just all just review from what we just said earlier, where we're just going to set the 0 position as the equilibrium length that's stretched by delta L due to gravity. And then we're going to consider an additional periodic external force. Ft is equal to 2 cosine of 3t. So I'll say 2 cosine of 3t. So we're adding an external force. This is like this is a vertical spring mass system that's hanging on this off the ceiling, and then there's like an earthquake shaking it, or this could be inside of a box and you're shaking the box. And so that's the differential equation that will describe this. It just doesn't have a damping term. And with the K, with the M and the K that we just found, so M is 1 like that right there. So it'll be x double prime. And then the K will be equal 9. So it'll be 9x is equal to 2 cosine of 3t. And then you're going to solve this. So you're going to do the homogeneous solution. So your homogeneous solution is going to be using the characteristic equation. It's going to be r squared plus 9 is equal to, let me use blue because I always use blue, is equal to 0. That's the characteristic equation. And you're just going to notice that this will be complex. So the r squared is equal to -9. Therefore, your r is going to equal plus or minus 3i. It's pure imaginary, and it's going to just be equal to this, which gives us our homogeneous solution is going to be C1 cosine 3t plus C2 sine 3t. And the particular solution is going to be from your left-hand side, or the right-hand side. So our right-hand side looks like this. So from that, our particular solution will be equal to a cosine of 3t plus b sine of 3t, right? But there's an issue, right? What do we have to do to this? This entire thing matches this term by term. There's literally no hope of this solving this non-homogeneous differential equation because it's exactly the homogeneous equation. So that means that we'll have to multiply by t. So you have an extra factor of t that you can multiply to this. So that gives you your particular solution is going to equal t times the a cosine of 3t plus b sine of 3t. And that will be your correct particular solution form. And we know how to solve this, right? So you'll have to like do a bunch of math by taking the derivative of this, the second derivative of this, and you'll eventually get. So I'll just leave this blank, and then and maybe I'll do it when we do return. But eventually you'll have to do that, and then you'll get like this as your particular solution. This is going to be the purple one. And then you'll have plus, you have a, your homogeneous solution, which is going to be this right here. And I'll just like jump to the and then of course there's initial conditions. So it's saying the mass is displaced by 1 centimeter downwards and then simply let go. So as an initial velocity of 0, apply those initial conditions, you'll get that this is equal to 1 and this is equal to 0. And so your official solution at the end will just equal this plus the 1 in front of this, just be cosine of 3t. And then this is 0. And so this right here is the green graph. The red graph is really just this piece right here is the red graph. So there's a particular solution here that got multiplied by t, saying that you have a sinusoidal function, but the t is actually going to grow the further you go in time. And that's what causes the motion to actually vibrate with a much more higher amplitude as you go higher and higher and higher. And the reason is because the forcing frequency that you actually used was 3 here, and the natural frequency was also 3. And so when you vibrate at the same frequency as the natural frequency of the system, there's something called resonance that occurs, and that will cause it to vibrate much more larger and larger and larger as time progresses. But we'll have to talk about that more when we get back, this idea of resonance. But you see that because basically you have to multiply by t to your original particular solution, and that multiplication by t is going to cause a solution that's going to have a sinusoidal with a much more higher amplitude as time goes on. All right, I have office hours, but we have to go upstairs because the room down here is the department asked if they could just take it from